So in the previous video, we discussed the least squares problem and discussed the notion of distance and orthogonality in general abstract setting, as well as the studying Gram matrices for unit products. So this time we discussed the spectral theorem and the singular value decomposition. And this will be our last lecture for the course. So in the extended version of the course, we also talk about differential equations, but in this shortened summer session, it goes beyond that. So a reminder, they have an inner product of a vector space on a vector space V is a bilinear map that sends V cross V into R, which is distributive, commutative, and positive. It satisfies three key properties. Distributivity, which means that you can open parentheses and as follows. It's commutative, so V in a product with W is equal to W in a product with V, and it's positive, so vector V in a product with itself is greater or equal than 0, with equality only when V is equal to 0 identically. On Rn, we can conveniently in the basis, in the canonical basis of, well, in the basis of given basis with basis vectors EI and E1 through EN, you can write it as such, right? So A is the Gram matrix of the inner product. So V in the product W is equal to V transpose A times W. So does a matrix actually define an inner product? So for any matrix A, we can write the formula, right? We can multiply it by the row vector on the left and by the column vector on the right. It always satisfies distributivity, right? Just by rules of multiplication of matrices. It also satisfies commutativity if and only if A is symmetric, right? So if you write it as, if you do the transposition, and if transpose matrix is equal to A, then VW is equal to V to WV. And then when does it satisfy positivity? So last time we talked about the 2x2 matrix. It was positive if the eigenvalues are positive. Right. Let's talk in more details about eigenvectors of symmetric matrices. As we know, eigenvectors with different eigenvalues are linearly independent. So for a symmetric matrix, eigenvectors with different eigenvalues are in fact orthogonal, right? So since M transpose is equal to M, for every vector V, we have V transpose times M is equal to M times V everything transposed. And if Vi and Vj are eigenvectors with eigenvalues lambda and lambda j, then we can do this calculation. So Vj transposed M, Vi transposed M Vj is equal to lambda j times Vi transposed Vj, and we can also write this as sort of, so that's one computation. Another computation can combine M V transpose and write it as M V transpose, and it will be equal to lambda I Vi transpose Vj. Right. So if these eigenvalues are different, then it follows that these vectors are orthogonal, right? Because it's the same thing. It's the only way to reconcile these two situations. Now the spectral theorem. A symmetric matrix M has all real eigenvalues and an orthonormal basis of eigenvectors. Let's prove it. So for any real basis of eigenvectors with different eigenvalues, so those are already orthogonal, and those which are not, right? So which have a eigenspace of dimension bigger than 1, we may use Gram-Schmidt procedure to replace the basis with an orthonormal one. So it's done by constructive proof. So it's enough to find a basis of real eigenvectors. So the first task would be to produce a single vector. So certainly M has a complex eigenvector V with complex eigenvalue lambda, at least one of them. So let's denote with the symbol dagger, right? It looks like a long knife. It will also look like a cross, but it's called dagger. The operation of taking transposition of the matrix and complex conjugation of all of its elements at the same time. Now, lambda V dagger V is equal to lambda V dagger MV, and is equal to MV dagger V, or is equal to lambda conjugate V dagger V. So the algebraic manipulation with this dagger symbol are the same as with this transposition. Only now, if eigenvalue is complex, after we apply the dagger operation, we use the complex conjugation of lambda of the eigenvalue. Now, V dagger V is the sum of squares of lengths of entries of V, and because it's the V dagger is just a vector which is formed by complex conjugate components of V. It is positive and non-zero, and therefore lambda equals lambda conjugate is a real number. Right. So it says here that this is equal to that, right? Therefore, from here it follows that lambda is equal to lambda bar because the V dagger V is non-zero. Now we know that there is a real unit eigenvector with real eigenvalue. Consider the orthogonal complement V perp. And that is preserved by the matrix, right? Because if W transpose V is equal to 0, so then if you act with matrix M on the vector W and then transpose it, we'll get MW transposed V equals W transposed MV is equal to lambda W transpose V is equal to 0. So it's equal to 0. And then we can pick an orthonormal basis W2 through Wn inside the orthogonal complement. And then we have a basis V, comma W2, W3, etc., Wn. In this basis, the matrix M has the form here. So like we have the first row and the first column have only one element in them, so V transpose MV. And then the rest of the matrix is formed by the corresponding entries, right? So it's Wi transpose M Wj, where I run from 2 to n. So this lower right block is a smaller symmetric matrix, and we can continue and do the next step by induction. So that's the theorem which we have proven that the symmetric matrix M has all real eigenvalues and orthonormal basis of eigenvectors. Let's reformulate this in slightly different fashion. So a matrix O is said to be orthogonal if its transposition is equivalent to its inversion, right? So, or you can write it as O transpose times O is equal to identity. So equivalently, if the columns are orthonormal, equivalently that if rows are orthonormal. Now, here's another theorem, which is the reformulation of the spectral theorem. So if M is symmetric, then there is a orthogonal matrix O and a real diagonal matrix D such that M can be decomposed into ODO inverse, which is the same as ODO transposed. So in other words, every product, every symmetric matrix, it can be decomposed in the product of the orthogonal matrix. It's a diagonal matrix which is conjugated, right, which is multiplied by the orthogonal matrix on the left and the same orthogonal matrix transposed on the right. So the columns of O are orthonormal vectors of M, right? Yeah. And then the diagonal matrix D will be formed with the with the eigenvalues, with the eigenvalues of matrix M. So we can write this more specifically. So if M is symmetric, then there is an orthonormal basis Vi and real numbers lambda I such that M is equal to lambda 1, V1, V1 transposed, plus and so on, plus lambda n, Vn, Vn transposed. Now, these vectors Vi are eigenvectors with eigenvalues lambda. So, and then by orthonormality, the squares of so Vi transpose, so it's a matrix, so square of this matrix is equal to this matrix itself, right? Because you can write it like this. Right, so Vi transpose squared multiplied by Vi transposed. Now recall that this is equal to 1. Right, so this is equal to, again, Vi transposed. And this is equal to 0 when I is not equal to j. Okay, now suppose that M is symmetric, then it is true that for every vector W, this combination W transpose MW is greater or equal than 0. So it's an equality only when W is equal to 0. So if and only if M has only positive eigenvalues, right? So it is true for if M has positive eigenvalues, then the statement above is true. Right, so we can take an orthonormal basis Vi of eigenvectors for M with eigenvalues at lambda I, and then because it's orthonormal, then Vi transpose M Vi is equal to lambda I Vi transpose Vi, which is lambda I. So if any of those lambda i's is less or equal than 0, then n is not positive. And on the other hand, we can explain sort of in the proof in that direction, we can expand W in this basis with coefficients Wi, right? And then if we evaluate this formula here, so W transpose MW is equal to sum of Wi Vi transpose M, sum Wi Vi is equal to sum of Wi squared lambda I. And this is definitely positive if all lambda i's are positive and W is a non-zero vector. Now let's talk about square roots of matrices. We can define square roots of positive matrices. So as well as for the positive symmetric matrices, right? So if you have A is the spectral decomposition of A in terms of OD, O inverse, right? With the D having all non-negative entries, then we can write square root of D for the diagonal matrix just by taking the square roots of its diagonal entries, right? And then we can define square root A to be like this. So it's square root D conjugated from the left from right with this orthogonal matrix O. So then the square root A is again symmetric and positive, right? And if you take the square, right, you'll see that you'll get the matrix A back, and because of the orthogonality, right? So square root A squared is equal to O root D here, O inverse, O square root D, O inverse, right? And this thing in the middle is equal to 1. So it's equal to O D O inverse. Now, we could ask ourselves how big or small can be the norm. So that if you take a vector W and apply and calculate the norm of AW and divide by norm of W, what is the range of this quantity? So how small and how big it can be. Now, if A is symmetric, then we can take a basis of orthonormal vectors, and we can write W as a linear combination of the basis vectors, and then same we can do with AW. So it will be Wi lambda I di sum over all I. And from here, we can see that this quantity here, the absolute value of PW over W, or the norm, is equal to square root of sum of the squares. And if you look at this ratio carefully, you see that the maximum value it may take is the maximum of absolute value of lambda, right? It's basically if whenever the corresponding W is equal to 1 and all others are equal to 0, or the others, well, maybe not necessarily 1, some value and the others are 0. And then also the minimal one. So this thing is ranges between minimum of the absolute value of over all eigenvalues and between maximum of the absolute value of all eigenvalues. So that was the story about symmetric matrices. How about for matrix A in general? Maybe if it's not a square matrix. So we can define absolute values squared as AV transpose times AV. So it will look like V transpose AT, A transpose V. So now AT transpose A is symmetric, right? And square. And of course, it's non-negative, right? Because this is the same as AV squared. We just saw it above. So it has a symmetric non-negative square root, which we call B, square root of A transpose A. And then we can reduce the problem to the symmetric case, because if you write AV squared as V transpose A transpose AV, or V transpose B squared, according to our definition, which is of course the same as V transpose B transpose B, V, or BV absolute value squared. Next story is singular values. So let Vi be an orthonormal basis of eigenvectors for ATA with eigenvalues lambda I. We can order them so that lambda 1 is greater or equal to lambda 2, greater or equal than, and so on. And as we know that they're all positive, right, because it's a symmetric matrix. Now let's denote sigma I to be square root of lambda I. So these are called singular values of A. So singular, yeah. Now, since the dot product of AVI with AVJ is equal to 0, when I is non-equal to J, and if they're the same, then it's equal to lambda I, or it's equal to sigma I squared. So the vectors Vi are orthonormal, they form an orthonormal basis whose images are also orthonormal, images under the linear map AA transpose. We can now rescale the images of the of those vectors to be orthonormal, right? So we divide them by sigma I, because remember sigma is the square root of the eigenvalue. So it's UI is those normalized vectors, and we can extend the UI to an orthonormal basis. Now, matrices U, capital U, and capital V, which are formed by columns of the basis vectors UI and Vi, are orthogonal. U transpose equals U inverse, and V transpose equals V inverse. Now, the matrix sigma, which is U transpose A times V, is diagonal, whose entries are sigma I. And you can multiply by U on the left and by V transpose on the right, and then you'll get that A is equal to U sigma V transpose, right? So now sigma will be the matrix whose diagonal elements are those singular values. And that provides us with the singular value decomposition of the this matrix A. Right, so it's U, which is this matrix whose columns are the orthonormal basis of images of vectors Vi times the diagonal matrix of singular values or square roots of the eigenvalues times the transpose matrix of columns of basis Vi.